part 2. We'll look at visual measurement. So we're looking at examination, and the first kind of examination is visual examination. Now, we have light booths, standard light booths that we use that have standard light sources in it to look at color, to make everything standardized and everything look the same. But before that, colors were evaluated using real daylight. Remember, one of our older instructors that's retired now used to work for Goodrich, and they were in Cleveland. They would make up samples to take to the auto industry, so they'd drive up to Detroit with their standards. They'd get to the purchasing officer's office, and they'd see them, and then they'd take all their standards, go outside, find a car that's the right color that it should be, and then match their standards next to the car. They do it outside. We talked about daylight is not the same all the time, so that can cause some variations. The standard was to place, if you were inside, the samples in the light of a north-facing window. And you'll see, helps to wear a white shirt and a cheesy tie there. There you go. See, that's how you have to do it. To wear the white shirt there and the cheesy tie. Kind of hard to see there, but there's a sample he's looking at, the light coming from the window so that it's illuminated, and he's making his visual observation there. More standardized now with our light booths. It's always better if you're doing some kind of evaluation to keep everything as consistent as possible. Like I mentioned, there's standardized light booths. We have several in the lab there. They typically have 3 light sources in them, 4 actually, because they have UV light in them too. But 3 visual light sources. One is daylight, the simulated daylight. Ours is D65. There's also a D75. And what those numbers represent, the D is for daylight. The 65 stands for 6500 Kelvin. Remember what Kelvin is? Absolute temperature. That's how we measure how much energy comes off of a light source. Characterize it by the temperature of that light source. So there's one that's D65 or 6500 or D7500. Most common is D65. We also have an incandescent light bulb. In our booth, it's called Horizon Light, and it's 2300 K. So you can see it's a different temperature. And finally, we have cool white fluorescent. This one here is 4400 K, but there's several types of fluorescent bulbs. There's warm fluorescent, there's daylight fluorescent, there's all kinds. So if your customer has a very specific fluorescent light source that they want to use, you can get that and put it in your light booth so you can look at your samples under that particular light. Here is a fancy drawing of a light booth, and that's how we look at samples. The light is up in the top, so the light is going straight down. We generally look at it at about a 45-degree angle. Buttons up there represent the different light sources we can change it to. Industry, a lot of times, they'll have a relatively small room, maybe from here to the wall, and they'll have some big lights in there with a big table. You walk into the room, the whole room basically is the light booth. I know when we go to a tour of Shulman's and Bellevue's has a setup like that. Maybe Poly One also. And that's really the same as a light booth, but you can kind of think of it as a big light booth. Especially if you're doing automotive type work, they're really specific about those conditions. And the whole idea is that it's consistent. That's how they want to look at the light and make all their determinations with the same parameters. So you would like your viewing conditions to be stable over time. And not only should you use the light booth, but you should calibrate it. You can measure the light that comes off of it. They have preventative maintenance type procedures where you change the bulbs every so often before they change. Sample conditions for which the samples are being specified needs to be constant. The neutral background, it's kind of a white cream color background. The reason for that is if you have different colors around a color, it can affect how we see it. So you want it to be neutral so it doesn't affect it. I mentioned before that the samples should touch. so we can see the difference easier. Should be uncluttered viewing area. I hate to admit it, but our lab sometimes doesn't do this. Is you shouldn't have a bunch of junk piled in your light booth, or your lunch in there, or magazines, or whatever. It should be empty, except for your standard and your sample you're looking at. The ASTM, which is an organization that sets test specifications, does have a test method for visual examinations of standards. Or not everybody has spectrophotometers, so there are procedures for correctly visually evaluating standards. It lists the light sources that are needed, like I mentioned, in the light booths, and then the photometric conditions, or how bright the color is. So you can take a light meter like you would use for photography and put it under your light booth and see if you have enough brightness from your light booth. You can see there the standard is between 75 and 175 foot candles, which is a measure of brightness. The geometric conditions is overhead lighting and viewing from a 45-degree angle. And our background is neutral gray and uncluttered. So that's the way we should visually look at our samples. And ideally, you should turn the rest of the lights off in the room when you're doing it. That's why they have those rooms, because then you don't have to worry about any other lights being on. Even in our lab, ideally, when we look at samples in the light booth, we should turn the other lab lights off, because they could contaminate, if that's the right word, the light that goes into the sample. You know, the lights in the lab are fluorescent lights. If you want to look at your standards under daylight, if some of that light from the outside gets in, it can change the characteristic of the light. Let's look at the next slide here and see what you think. Is she looking at or evaluating samples correctly? What's she doing correctly and what's she doing incorrect? What's she doing correctly, you think? Putting them together, yep. She dressed right? Yep. She's got a white lab coat, so that's good. You wouldn't want to wear a bright red Ohio State jersey, for instance. Not that I can understand why anybody would wear such a thing anyway. You wouldn't want to do that in color matching, because that can, believe it or not, affect what the color looks like. Of course, that also makes you wonder about your judgment, but that's a different problem. What else can you say? It also looks like the light's on in the room. You know, that's not a good thing. So she's doing some things right. She's using the light booth. So we're using our standard light sources. We got our neutral color background. Wearing neutral color clothing. Mentioned that. The samples are touching. Like you mentioned, that was good. Looking at two samples. 45-degree viewing angle. She's sitting down and looking at it right. That's good. But there's a few things that are questionable. The light booth had a bunch of extra samples in it. That's not a good thing. You only want the two you're interested in. The samples are on the edge of the booth, so light from the room lighting can interfere. It's best to turn the room lights off when using the light booth, like I mentioned, and have your samples or at least have your samples pretty far in the booth. And they say you should have your samples laying on the bottom of the booth. But it also sometimes is good to hold them and turn them as you look at them, because you can see different things by looking at them at different angles. I mentioned last time that there's some directional component to how you can see colors. It can look different under different directions. So that's visual observation. Again, there's correct ways of looking at colors under the lights visually, and there's incorrect ways. So it's best to do it the right way, because you can get the wrong result if you do things incorrectly. When we use instruments to evaluate colors, in the color business, the type of instruments that is normally used is a spectrophotometer, not a colorimeter. A colorimeter doesn't do as accurate a job and doesn't give us as much data as we can get from these spectrophotometers. And the instrument makers like it better too, because spectrophotometers are a lot more expensive to buy than the colorimeters. Instruments that measure light reflected from the surface of an object or light transmitted through an object are called spectrophotometers. That's the other thing about a colorimeter. You can't measure transmitted light. You have to only measure reflected light. Used for many analytical purposes, not only color matching. We can use it for identifying certain colorants, certain materials in a mixture, that sort of thing, that uses other wavelengths besides just the visual. All we're really interested, I wouldn't say all, generally we're interested in the visible spectrum from about 380 to 780 nanometers, say 400 to 700 roughly. There are other cases where we might be interested in higher wavelengths. That would be the infrared region. That we're putting, say, one of the applications where that's important is roofs on buildings. And mostly roofs on buildings are, what color? Industrial buildings, say. You know, flat roofs are black, right? What's the problem with black? Yeah, heat buildup. If you could get a black that can reflect infrared heat, you know, the energy in that infrared region, so there's not as much heat buildup, then that roof would result in less air conditioning costs, for instance, because the building doesn't heat up as fast. And there are, and black is the color they work with because it absorbs the most energy, there are companies that make IR reflecting blacks or IR reflecting pigments, so they're interested not only 780 but much higher wavelengths to see what it reflects. So they have special spectral photometers that measure that. There is some applications for that, but they're special applications. So here shows the individual components of our spectrophotometer. We must have a sample, our optics and illumination, some kind of dispersion. I mentioned it doesn't necessarily have to be a prism. Some kind of detector. You'll see there's two main types of detectors that are used. Computer that processes the signal, and then we need to output that information somehow so that we can use it to make our color decisions. This should be familiar to you, how you get the basic calculation of how our tri-stimulus values are calculated. Again, we started with our light source curve, just like we did in our homework. Light source times the object times the observer. Remember, we have three curves now for the observer, and that results in tri-stimulus values, capital X, capital Y, and capital Z. And then you'll see later classes that we can put those into LAB numbers, which are very useful for making color matching decisions. So again, we replace the eye and the brain of the observer with the instrument. The main components are our monochromator system, which means it separates the light into its different wavelengths. Some kind of light source, and there's several different ones that are used. Detector, computer, software, and there's a lot of companies that make different kind of software, either for quality control type applications or actually color matching applications. And then the part of the whole system that's usually omitted from this kind of discussion is a trained operator. One of the complaints of people in the color business, or at least concerns, is that many of their customers are buying spectrophotometers because, hey, we can buy these fancy instruments that can give us numbers about the colors, not subjective, and it can, you know, tell us our colors are good or not. They don't train their people to use them quite correctly, and then you get very incorrect results. You've seen something like that before? Yeah, and that's not just a problem with the color spectrophotometers and the software and that sort of thing, or a lot of things in industry. Think of, you work in industry. How well would you say you're trained to do your job? Very well or not so well? Sometimes not at all, right? You know, the instruments are great, and they do a great job of measuring what you give them, but if you don't present it right, present the sample right, or it's not a good sample like I mentioned before, it's not going to give you good results. So that could, you know, when people look at numbers, unfortunately, like they're absolutely right, even though they may come from a bad source. You know, the old adage about computers, garbage in, garbage out. I mean, the computer does what it's supposed to, but if you give it bad data, it can't come up with the right answer. One example of that is there's a company that sends out samples to lots of people that have spectrophotometers, and the whole idea is to see if they'll get the same numbers as everybody else. the samples are all the same that they send out, or at least as close as they can get. And then they take their readings at each plant, then they send the data back to the central company, and then they put all that data together and show what the range is that people get from it. They've gotten samples read very incorrectly. Example, there'll be a color on one side, and then there'll be white on the back side. Ideally, when you put it on the instrument, you put the colored side towards the detector, so it measures the color. But they've had instances where they flipped it over and put the wrong side facing the instrument, and obviously you're going to get a bad reading. You're not going to get the same color. If it's supposed to be a blue and you put white in front of it, no matter how good the instrument is, it's not going to give you numbers for a blue. So you have to be careful that you do that right. And there's a lot of simple things that somebody that knows what they're doing will do that somebody that doesn't know what they're doing won't do. And we'll talk about some of that later. So the eye of the spectrophotometer uses some type of monochromator system to dispense and select light, combining with a detector to analyze the visible spectrum of a sample. So that's kind of wordy, but that's what it does. Two types of monochromators now. It'd be the same as a prism is a monochromator. One's called an interference filter, and one's called a diffraction grating. But basically, they separate the light into its individual components just like a prism did. Now our light source, there are some requirements for it. Now it doesn't have to be one of the standard sources. We talked about the standard CIE sources, but our light source doesn't necessarily have to be one of those. But what it must have is output in all wavelengths in the visible spectrum. So it has to have some output in all the wavelengths. From that, we can manipulate it mathematically to represent any illuminant. So any illuminant that we want it to be converted into, we can do that by just changing the numbers. Remember, illuminants are just the table of numbers anyway. Okay, the source is the actual light. So the actual light that's in our spectrophotometer, there's two types that are generally used. One is called a xenon lamp, and the other one is a halogen tungsten lamp. A halogen tungsten lamp is just like a projector bulb, for instance. A xenon lamp is a flash lamp that flashes when it takes its readings. So there's two types. The key is that it's consistent all the way through, from time to time, so that if you make a measurement today and then you make a measurement 6 months from now, the output from your light source is the same. And that's always adjusted during calibration so that you always get the same results. You wouldn't want to take a measurement today and then a year from now take the same measurement and get completely different numbers. The detector has to have some requirements. Again, it has to have response in all wavelengths, and we can manipulate that output to represent the standard observer, or how our eye sees color. There are two types of detectors normally used. One is called a photomultiplier tube, and the other one is called silicone photodiode. You can see from this graph here, there's quite a big difference between the response of our eye. It has that bell-shaped curve in the center. That's the response from our eye. That's what we used in our calculations that we did. The other two, silicon photodiode and the photomultiplier tube, is completely different than our eye's response, but both of them have response in all wavelengths in the visible range, so then we can use them and manipulate things mathematically. Models how our eye sees it. Again, it doesn't do it exactly the same. We have to model it somehow, and whenever we do that, we have some type of error involved in it. Maybe a little bit, maybe a lot. It just depends on our model. Another important characteristics of spectrophotometer is their measurement geometry. There's a couple different kinds there. You need to determine what that is to make comparisons. So the measurement geometry determines the angles of illumination on the sample and the angles of observation for the measuring instrument. Two major types are used in industry. One is a 045 or 45-0. Those will refer to the same type of geometry, just backwards. Or an integrating sphere. and sometimes that's referred to as D/0 degrees. That's 0 degrees there, or the other way around. But those are the two types. If somebody asks you on a test, for instance, what are the two types of measurement geometries, those would be the two types that they would be. 45-0 and 045 are the same thing, so that wouldn't be two types. That's the same type. That's something that I think students in the past have gotten confused about. And we'll show what the differences are between them. The first one here is the 045. Where that name comes from is there's a 45-degree angle between the light source and the detector. Whether the detector's on top or the light source is on top, that's what shows the 45-0 or 045. Doesn't really matter for how it works. It's the same thing. We have our light source. It shines on our sample, and then we take a measurement at a 45-degree angle. So the only light that is detected by this instrument is the light that goes on this particular angle. And that's important when we talk about color and appearance. This is our spherical geometry, the other type, and this is the type that we have in our lab for all of our instruments except for maybe one of the handheld units. And the difference here is we have a sphere, this isn't just a circle, but a sphere called an integrating sphere, that when the light shines into the sphere, it bounces off our sample, and then the light from the sample bounces off the integrating sphere, so that all the light that comes off of the sample is collected. It's not only the light in a certain angle. So no matter what angle the light is diffused off of the sample, it's collected by the detector. The light shines in, hits the sample, and then light bounces off in many different directions, and the detector catches the light no matter what direction it came off on. Because the sphere is white, the light bounces around until it finally hits the detector. It's not only at one specific angle of viewing. Our first kind of geometry, the 45-0, measures what we call appearance, so how it actually looks to our eyes. So it reproduces the best how we actually see a particular sample. The integrating spheres, and we can use those two different ways. One is called specular component included, which collects all the specular light. So if we have that, all the light that comes off of the sample is collected. Or we can have it set for specular component excluded. There's a port or a door in the side of the integrating sphere at a 45-degree angle that can be open so that the light that goes at that particular angle goes through it, so it's not collected by the sphere. The idea is it's similar to the 045 measuring method. But this is what it looks like. If we have specular component included, like the bottom here, the specular reflected light hits the sample, bounces off, hits our sphere, and then is detected by the detector. In our excluded, specular component excluded arrangement, that specular reflected light hits the sample, bounces out through this opening, and is not collected. Now, it's not exactly like the 045, but it's closer than the specular component included. So why are these different instrument geometries different? First thing we need to do is look at what makes up appearance of an object that we're looking at.